Sure is pretty kind to us.
All right. My name is Machiavelli Davis, and we're at Prophase Biostudios here with Justin Atkin today. We've got Trevor Titman and Joshua here today to chat. The link has been sent out to some other people. If you don't know who I am, I started Prophase Biostudios, which is a federally recognized biohacker space, charity, educational, community biotech lab, and we have events where sometimes we talk to cool people over the internet. And, this is Justin. Justin, would you like to introduce yourself?
Yeah, well, so, I mean, you got my name already. I don't know, I tend to do cool things, and I mess with biology things sometimes, and I'm kind of like your stereotypical mad scientist.
All right. Did anyone want to introduce yourself? You don't have to. Okay, they're good. So, Justin, when I saw your stuff, I was like, man, that when I was not until now have I figured out how to set everything up so I could do all of the things that I wanted to do. And just it's been painful for the 10 years to be yearning to have my own lab and to do all of the crazy things that I want to do, and the little experiments and the DIY, how to make a supercapacitor, how to make graphene out of with a laser from a DVD drive and stuff. So I really admire your situation. Can you tell me how you figured this out? What was your starting place in all of this?
My starting point was I was about 14, and I finally talked my dad into letting me set up a little lab in the basement. And it started really simple. It was before I really knew much. So the way I would do it is I would kind of come up with an experiment with whatever I could find lying around. I really liked copper chemistry. So I was doing a little bit of electrolysis. I was doing a little bit of actual chemical stuff. And so as I would learn, and as I was learning to understand chemistry, I would make videos so that I could show other people, because I'm like, well, this is cool. Somebody else might like this.
Yeah.
And then I was kind of just hunting around looking for cool things to do. And I stumbled onto a device called a fuser.
Yes. With Farnsworth there, no?
Yeah, which is basically the first fusion reactor. They're incredibly simple in theory. And to build I could build a demonstration model fuser in an afternoon at this point. But the first time I did it, it took me a year worth of tinkering with it to get it to work.
You could build a demonstration model in half a year, you said?
In a year. Well, that's not true. I got it functional in a couple of months. I got it truly working well in about a year.
What did you need to do in order to? What are the essentials for making a fusion reactor at the scale that you did it at?
So I was going to move on to an actual fusion producing reactor, stainless steel parts, all that kind of stuff. But for a little demonstration model, it's really, really simple. You need a transformer out of a microwave. You need a decent vacuum pump. And a couple of high voltage diodes. A variac is good to be able to control how much voltage you're getting, but past that, that's basically it. It's just a chamber. I used a mason jar because that was what I had on hand. So mason jar, and so you've got an outer grid, which was just a turn of wire that kind of went around the outside, and then you've got an inner grid. And you just put your DC high voltage between them. And if your pressure is low enough, the whole chamber will glow.
So what is the gas in the chamber? Is it hydrogen or deuterium or something?
So if you're going for actual fusion, you use deuterium. But if you're just going or something to glow, then all you need is just anything. Like when you pump it down, it'll just glow just from residual oxygen and stuff, and nitrogen for the most part. But you can add in whatever gas you want. Recently, I was trying to build a titanium nitride sputter coating device, and
Okay.
and so for that, I was using a mixture of argon and nitrogen. But I mean, you can use all kinds of different stuff depending on what you're trying to do.
All right. When did you first build the demonstration fusor?
So when I was 14, so I was in grade 9. Yeah.
Okay. Your dad was like down to buy all that stuff for you,
No.
or did you have your own?
So I would work as it was fun. I'd work fixing old white people's computers. Because they had no idea what they were doing. So I could I'd spend the afternoon I'd install Windows and reset the router, and it'd be like $200. I was like, yes.
Right.
So I do that. I'd work odd jobs just to save up whatever I could. And my dad was is a builder. So I would, whenever he would,
Okay.
so a lot of the times when he'd get a new property, there'd be some stuff left behind. Be that like an old fridge or whatever. So before he throws it out, I'd go onto his sites with a couple of tools, cannibalize the whole thing, get the couple of pieces that I'd need, and then I was good to go. But overwhelmingly,
All right. So,
I did it myself.
but what would motivate you to do such a thing? Where does your sense of motivation or interest or drive come from, and how does it direct what projects you choose to ultimately do?
So back then, it was just sort of infinite curiosity. I'm like a sponge for information. I love learning. It's like my favorite thing to do. So, and I think then, because with fusion and stuff, it was such high level science, and it was when I built the demonstration model, I was like, okay, this is just going to be cool. But once I did that, I'm like, I could legitimately build a nuclear fusion reactor at while I was in high school. That seemed like, I'm like, yeah, that's a thing I'd like to do. And one of the aims of the project was I was going to use the neutrons that the reactor produced to irradiate copper. Because when you irradiate copper, if you can make it radioactive, some of the nuclei will decay via positron decay. So I would literally be making antimatter at home.
Yeah.
Which I just thought would be so cool. Is it what?
Is it dangerous?
Oh, absolutely. They're so dangerous, it's ridiculous. But that was one of the reasons I liked it, because it made me learn how to be safe with these things, because high voltage will kill you, radiation will kill you, your chamber blowing up will kill you. So if you can learn how to be safe with that, you're way better off. I mean, there was
Illusion being kill you, will kill the people around you in the same building as you.
I'm sorry, I couldn't hear that thing cut out.
He's asking if a reactor you built had a failure catastrophically, what would the blast radius be?
So it's not that kind of a thing. It's not like fission where you're basically trying to make it not blow up the whole time. With this thing, as soon as it loses power, it stops. And the biggest problem is just the thing depressurizing, and because it's for an actual fusing model, you are using stainless steel, and there is no amount of radiation pressure that's going to blow that up from a fuser. They're not that powerful. They have an efficiency of less than 1%. They're not useful for fusion. They're useful as a neutron source. which is kind of nice because the only other neutron sources are from fissile materials where you put like americium next to beryllium and you'll get neutrons. This way, it's on and off switch. So when you don't want neutrons, turn it off. And it's really not an efficient fusion reactor. Like over the years, I've devised numerous new kinds of reactors that I've seen no evidence for previously, and I'm like itching to build them, but they're just too much of a pain, and I just don't have the stuff for it at the moment.
Okay, so I'm curious about two things. Like, if you, well, maybe three things on the fusion. One, when you made the neutrons and the positrons, will you be like determining whether or not you made positrons by building like a cloud chamber or some other kind of thing like that? Or, and is it, what, do you have any plans theoretically on capturing or storing the positrons?
So
And go ahead, go with those two.
So I had no intention of capturing positrons. To do that, you need crazy magnetic fields and superconducting wire, which there's not a chance that I could work with.
Okay.
As to measuring it, it's actually pretty easy. If you hold a Geiger counter to your piece of copper, if it's radioactive, it's producing positrons.
Oh, yeah.
Just because there's only two there's two or three isotopes of copper that are stable, and they're always the one that would produce positrons on decay would always be present if you've managed to make it radioactive. But the way I would have looked for it specifically is I got this thing. It's called a gamma spectrometer. So it's the same as your usual like light spectrometry stuff, but it gives you the wavelength of the gamma that's coming off of it, so you're able to see a very distinct positron peak. So I had all sorts of detectors. I had a neutron detector. I had several Geiger counters, and yeah, so I mean, it's just all kinds of very delicate detection stuff. Bubble chambers aren't super useful because they don't actually give you any like qualitative data. They just kind of be like, yes, there's radiation there.
Okay.
But yeah, so that was sort of my yeah. There was a lot of like safety stuff that was going into that. Like I was building like a wall full of borated paraffin. So you get like paraffin.
Oh,
yeah, you get like paraffin wax. Throw some borax into it, so that when the neutrons hit it, they slow down.
Yeah.
And also, just because of the way my house was at the time, like my dad built it, and it was this big. He actually built an extra room specifically to be my lab, and it was right under the garage. So it was basically a foot of concrete on all sides. So, and it was big enough. Excuse me. It was big enough that if I put my reactor in the back corner, there's about 20 feet before you hit any of the other walls. And so these kinds of things work on the inverse square principle. So the further away you get from the thing, the danger drops off exponentially. So at about 30 feet, you're totally safe. So plus all the shielding and stuff that I was putting up around. So like lead for the X-rays, borated paraffin for the neutrons, plus the foot of concrete on all sides. Like as long as I wasn't in the room when the thing was on, I would have been totally safe. And I was originally going to build like this whole control room in the other, like down the hall kind of thing, so that I could control the thing without having to be anywhere near it. But yeah, so that was my fusion room.
Okay. So I just want to mention, Austin, your microphone is on. If you're not going to use it, it's better to not cough into it.
Hey, what, cough?
Yeah, Austin.
I don't think I was coughing.
I heard there were a number of coughs that came from the Austin Square.
I'm sorry.
Okay, That's all right. We've got a question back here. Josh, go. You can go ahead.
Have you noticed any changes to your body physically? Because I was like wondering, like how many precautions you took, and you answered the question, and I was like just wondering, and you answered the question, but I was like, you okay?
Are you okay, Justin?
I'm perfectly okay. So what ended up happening, building a reactor like that is really, really bloody expensive. And so I rented, and also to get the parts to do it, you've got to wait for a lab to decommission some of them. So I got very close to an actual like fusion producing reactor before my dad finally like talked me out of it. He's like, dude, this is costing like copious amounts, and it's really dangerous. Are you sure you want to do this? So I never ended up going all the way to neutron production. So I was never like exposed to it. The only like radiation that I've been exposed to, I had a habit of collecting radioactive materials for a little while just because I thought they were cool. So I have like a little box, that like a shielded box with like my 2 or 3 little samples in there. Like I've got some thorium, I've got some americium. But I mean, no, I'm totally fine.
All right, nice. Is there anything you can foresee happening in your life that would line up with you, like carrying forward with this particular nuclear fusion project, or do you think you're too different?
So I've been thinking about fusion for a long time now. So I came up with a design fairly recently, actually. That is a totally new way of doing fusion. I've called it vortex fusion, where basically I form like it's like a little plasma tornado to compress the ions down. So yeah, and it would be like a little benchtop thing. So I would love to try it out, but there's a whole so this is what I mean. Like I'm so tempted to just go out and buy parts so I can build like a little demonstration model to prove the concept. Because if it works the way that I think it's going to work, the faster you make the thing rotate, the smaller the tornado should get and the tighter it should get. And I could demonstrate that with just plasma. So I could build the reactor. The problem is I've got so much other stuff going on at the moment, I just don't have time. So I'm hoping in the next like year, ideally, I'd get a chance to try it out.
Okay. Have you looked at studying the EM drive?
Oh, the thing that seems to run off nothing. Not really. I have a few designs of my own for like space engines. Like I had a fusion engine for a while that I was tinkering with. Although I'm a really big fan of the shoot a giant kite with lasers to make it go.
Okay.
I mean, what could go wrong with that? So we got to build giant lasers on the moon to propel our spacecrafts? Are you kidding me? Fuck yes, sign me up. Are you like? So yeah.
I mean, you still diet for that kind of thing.
Yeah, that's. I mean.
You could just mount mirrors at places too.
Yeah, but well, not really, because you'd lose a lot of the light.
Yeah.
Like, it would get scattered. Whereas with a laser, I mean, no matter how you try and do it, it's going to be really, really difficult. But I mean, that's sort of how you go. Yeah.
There was a Russian. I watched a video on this project or this type of project. Russian billionaire gave $100 million to like a company or organization to kickstart a program that with
to find intelligent life on other planets.
A laser.
Okay.
A laser kite thing.
A laser kite.
Yeah, Stephen Hawking and others recently just backed that project. So that's why I'm so excited about it, because they're going to send a whole fleet of tiny little. They're going to be like that big. Like the actual ship itself is that big, but the kite is like a kilometer across.
Right.
It's just this massive thing, and they're going to shoot it at Alpha Centauri. I'm so excited for that. Because the only thing that's more cool than that is either antimatter propulsion or a Kugelblitz, which, oh my god, I want a Kugelblitz so bad. Since it's a spaceship that runs on a black hole. So you literally get petawatt lasers and you fire them all at a spot so that there's so much energy in that one spot that it caves into a black hole. You keep it so the black hole is a very precise size, and so on its own, if you were to leave it alone, it would decay back into nothing in about 3.5 years. At that size, it's producing so much radiation. If you can aim that radiation backwards, you'd be able to not like get your spaceship up to like 0.9 C, which is just like stupid fast. So I'm a very big fan of that one, but it's going to be really hard to build. But I'd like to get around to it at some point, because it's an excuse for me to make a black hole, and then, you know, there's... I see nothing wrong with this.
They said theoretically that the laser kite sail can get to 1/5 the speed of light.
Mhm.
Yeah, I was very surprised by that.
Yeah, I'm really big on like next-gen space travel. I mean, because the only ways that we know to get up to that speed, or that we could easily get up to that speed, is nuclear warhead-powered spacecraft. Where basically you set off tiny little nukes behind your spacecraft, like once every, I think it was a couple hours or something, and just the explosions just push you kind of sequentially faster and faster and faster. So that we could using that, we could get to Alpha Centauri in like 45 years. It get you like 0.1 C or 0.2 C. The laser kite thing gets you to 0.4, and a Kugelblitz gets you to 0.9. Although I'm a big fan of the Alcubierre warp field, because then you can go faster than light, and then there's not much you can't do at that point. But I mean, that one is just ungodly difficult, because just the math involved is horrifying, and I want nothing to do with it.
You might have to set off nukes to create enough electricity to power those lasers to build a black hole, though. Like, I can't imagine how much energy that would take.
A lot. Like, a lot. Like,
Yeah.
like a lot. You'd need like a whole new power system just to be able to power the damn thing.
Yeah.
And it'd be a very, very big ship. So it would be a whole lot of nuclear reactors powering that thing. It is the kind of thing that if that thing were to crash, oh boy, would that make a very, very large boom. And it would probably screw up a planet, because you've just crashed a black hole into the surface, and that's not going to go well.
With a lot of fissile material, too.
Yeah, and once you've got a formed black hole, if that bumps into a whole planet worth of matter, that's no good, because it'll get bigger. So, yeah. Definitely some risks with that one.
How do you close a black hole?
You wait.
You wait.
You pray?
Yeah, it's one of those things that once you've formed it, there's no going back. You just wait. Make sure it's small enough that it'll decay in a reasonable amount of time, and hope like hell it doesn't come in contact with anything big.
Justin, is there any reason why we should be afraid of CERN for accidentally making a black hole?
No. The black holes that they could form, and since they've already done like very, very high energy tests and nothing's formed, you've got nothing to worry about at this point. But even if they did, the thing is so small that it would decay in a fraction of a second. Like it wouldn't have time to interact with anything, so it'd be like, ooh, cool, physics. But that's it. Like it wouldn't do anything dangerous. I actually did an interview with one of the researchers who works on like with Atlas and the Atlas experiment, talking about that and strangelets and all that kind of stuff. And she's like, yeah, there's not a chance that's going to happen. Like the sheer amount of energy that's required for that is several orders of magnitude higher than anything that CERN can produce, even with the size of their collider. Like just the energy is just astonishing.
Can you tell us about supercapacitors? How are you making these, and what makes you think that you can make them better than they have been made in the past?
So the reason that I know that I can make them better than the way that they're currently made is because basically everything on the market uses activated carbon. So the way a supercapacitor works is you've got your two plates, a membrane in between, and some electrolyte kind of moving between it. And the way commercial supercapacitors store charge is you move ions across the membrane, and they get stuck in and amongst the activated carbon. So the more ions can get stuck, the more power you store. But the problem with that is activated carbon, it's just like a loose interaction. It's the ions don't actually attach onto the surface, so there's no energy that way. They're just kind of there. And also activated carbon just doesn't have, like, it's got a lot of surface area, but not that much, really.
Okay.
So there's another kind of, so there's two or three kinds of supercapacitors. There's the carbon-based ones, which are just kind of like the loose interactions. Then there's semiconductor-based ones, where the ions actually like stick to the surface, and there's charge transfer and all this kind of stuff. And those reactions are about 100 times stronger. The problem is semiconductors are just that. They're not very conductive, so you lose a lot of efficiency in your cell. So what I work on are what are called hybrid supercapacitors. So they've got a carbon, but they've also got semiconductors. So rather than just one or two kinds of reactions, there's like dozens of different reactions all happening in the same cell to store the power. And so anything that uses graphene just sort of instantly works better, just because graphene is a very weird material, and it's got sort of semiconducting properties, sort of conducting properties, and because it's layered, rather than just kind of going near the surface, you can actually force ions between the layers and store power that way as well. So the things that I'm making take into account all of these things. Also, the stuff on the market uses usually sodium or potassium hydroxide as the electrolyte, which is fine, but it's also water-based, so it can dry out, and it can leak. And if it leaks, it's going to leak frickin' sodium hydroxide everywhere, which is not pretty. Whereas the stuff that I'm making, there's no water in them. They use a variety of different ions rather than sodium hydroxide.
What ions are you using? And are you using some kind of gel and water, or?
Yeah, I'm using stuff called dietetic solvents, which are super weird materials. Basically, you take two solids, like two salts, and you mix them and warm them up a little bit, and they turn into a liquid. And they'll stay as a liquid down to like -30 degrees. It's super weird. But it allows you to have all sorts of really high charges in there, because the more charge your thing has, the more energy it's carrying. Right? So if you use like calcium or magnesium instead of sodium, you're getting a 2+ charge rather than a 1+. So it can carry more power. So all that kind of stuff.
What is the mechanism by which the deep eutectic solvents, did you say it was? How do they stay? Because they're solid together, then you melt them, and then they stay liquid through a extremely wide regime. That's why they're called deep, right?
Yeah. So the way it works is you pick two different salts where the ions are totally different sizes. So when they melt, they kind of get mixed in and amongst each other, and they don't. They're like because of the way the shape is and because of how weird it is, it can't crystallize again. Just
Okay.
because the ions are in the way, so it stays as a liquid. And so you have generally two components. You've got a hydrogen donor and a hydrogen acceptor. So one of the really common ones is you use quaternary ammonium salts, so something like choline chloride or trimethylglycine, and then you use like any of a huge list of stuff like ethylene glycol, polyethylene glycol, glycerol, all kinds of similar stuff. And so yeah, I've just been exploring, making different ones and all that kind of stuff. And the ones that I've found seem to work really, really damn well.
Are all of these mixtures toxic to humans, or
No.
are they not?
So it depends what you use. I'm using stuff that is minimally toxic. Like if it gets in you, it's not going to be fun. But like, it's way less bad than the lithium batteries. Since lithium batteries are all they're organic based, and the organics themselves are carcinogenic or just so toxic it's disgusting. And also can light on fire, whereas mine can't. And the one I've been playing with recently is based on glycerol, which is glycerin. You can eat it, you can vape it, you can it's about as safe as it gets. So I mean I'm trying to make the things so they're as safe as physically possible.
Okay, so tell me what the process is here. So you get the deep eutectic solvent, and we're going to use like glycerol with some calcium salts mixed in, and is there two other metals in it?
Well, so you can use a combination of different things. So you can use like different deep eutectics mixed together, and form like way more complex solutions. It really depends. It's a lot of just trial and error and messing around with it. Like I can't tell you what's in mine because I am trying to make it as a commercial device, and to sell it because I'd really like to sell it to Tesla. That's the goal. Get it good enough that I can go, hey Elon, I got a battery that solves all your problems.
Right.
Right.
The big less toxic, the battery, or?
Yeah, they're as close to non-toxic as I can make them.
Right. Much better than lithium.
Yeah. So there's no lithium in it. They cannot light on fire. Like it would be very difficult to light the thing on fire when all is said and done.
Right.
Are there other people working on the same technology?
Mm-hmm.
Yeah.
There's labs all over the world trying to make a better supercapacitor, and the funny thing is, me mucking around in my kitchen, I'm getting better results than all of them because they're all like piddling away their time focusing on materials that are either ridiculously expensive or just so inefficient. It's kind of hilarious, to be honest. Like I'll read papers and they're like, we used like, whatever, and I'm like, why? Or like everyone's trying to use polymers because they're like, ooh, polymers are great, but no, they're not. They degrade very quickly, and they have way lower power ratings. Whereas I'm making stuff out of like, just simple, easy to get stuff, and it's working great. So.
Hey, I have a question. How do these supercapacitors, and maybe you could answer it for supercapacitors in general, how do their maximum charge and discharge rates compare to normal capacitors? Because I was thinking it would have to be slower because you have to have an ion migration through a layer, but I just looked it up and I guess that's not the case.
Yeah, so
Um,
a supercapacitor is really poorly named. They're a lot closer to a battery than they are to a capacitor. The only thing they share with a capacitor is how quickly they charge. So they're somewhere right between a capacitor and a battery where they charge quickly but discharge slowly. So I just posted a little thing showing where I was at, and I put like a little LED on it. They also run at a lot lower voltage than a capacitor does. Like capacitors usually run in the hundreds of volts, whereas this runs at like 2. So way lower voltage. The power comes out of it a lot more slowly. And theoretically, it can have higher power density than like a lithium-ion battery or virtually anything else. It's just a matter of getting that to happen.
and why is it that they can charge faster than a battery? Just because, I guess in a battery an actual chemical reaction has to occur, but here it's just ions moving around.
Well, so it's sort of just different reactions. So in a battery, it's all galvanic for the most part. There's very little in the way of like true capacitance.
Yeah.
Whereas in a supercapacitor, a lot of it works on electric double layers and that kind of stuff. Which those reactions are very, very, very fast. And it also depends what voltage you're charging the thing at. Like I saw one of the guys. So there's one guy who makes really, really good supercapacitors. Like he's already at where I'm aiming. And I'm like close on his heels at this point. So he was showing off one of his batteries, and he was charging the thing at 150 volts, and he was doing what was called tap charging. So he literally taps the lead onto the capacitor 10 times, and the thing's fully charged. Whereas, a battery that would take hours. And I mean, battery technology is getting better. Like, there's the new like supercharge functions on a lot of phones, so they can charge in like half hour or whatever. But I mean, mine would still be done in a minute. Like, it would never take half an hour to charge up. I mean, the ones that I've been making now, I make them real tiny because if it works unbelievably well at a centimeter square, it's gonna work. Just so much better when I scale, kind of thing. So mine charge in a second or two. It's really quick. So yeah, that's sort of how that goes.
What about the pattern between voltage as you go through the charge? Because like I know batteries are nice because they're kind of flat until you start to get low on charge, and then the voltage drops real hard. Whereas then capacitors, they're more like a negative exponential. Are they? Where do your supercapacitors lie?
So mine tend to sit like they start kind of high and then they drop off a little bit and then they kind of sit and drop way more slowly because they've got a voltage that they like to sit at. And I've seen I've seen bigger because mine are so small that you can't really see that happen for the most part because they're so tiny and they run out of charge so quickly that it's really hard to see that pattern. But I've seen bigger cells where you can very clearly see the point where they hit when they're like, okay, it will sit at 1.2 volts just for ages before it finally starts to drop off when it's running out of power. So it really is a lot like a battery and a lot less like a capacitor.
That's cool.
Yeah.
So I know that like Gabriel is working on flexible batteries, and you're just saying that these supercapacitors, you can make them out of glycerol and graphene and magnesium and calcium ions and some deep eutectic solvents. Do you expect that we'll be using supercapacitors like in implants in the future? Will we find some
That's the plan. So the overwhelming goal is to get my batteries up to the point where they could be used in an implant by June.
by June.
Yeah, that's the goal.
That would be wonderful.
I don't know if
Then
I'm
we-
gonna make it, but that's the plan.
Then we could put them in contact lenses.
No, God, no. Fuck. They're no, would not go well.
Okay.
You'd need to make a teeny tiny one, and oh man, that would be a nightmare. I'd basically have to make a totally different thing for a contact lens because it's so tiny, and you need to cram the energy into such a small space. I could do it, but it's a totally different technique. Like it's a different structure and a whole different
All right.
set of challenges. So I'm aiming for like the cells that I'm making right now. The one I'm aiming for June is 2 centimeters by 4 centimeters by 2 millimeters thick, and you know in the range of 50 milliamp hours worth of power.
Right. Wow.
Yeah.
So has this always been meant to be integrated with the hydroxyapatite and fibrinogen implant idea?
So all the kind of biohacking stuff has really been pushed to the back just because I've got bigger and better things on the horizon at the moment, and I just don't have time. Will I use supercapacitors in future implants? Yeah, absolutely. That's the point. The whole point of me making these things is because I'm frustrated with the way battery technology is, and I wanted to make something better. So yeah, it will definitely be used, but probably not soon by me, but definitely soon by other people.
Okay, nice. What about the? Can you tell us about your quantum dot formulations that you're selling on your website? Are these like where did this formula come from? Are they still available? What are they good for?
So they're at the moment.
And for those that don't know what quantum dots are, feel free to explain what you think quantum dots are.
So quantum dots are kind of cool. They're nanoparticles that are so small that quantum mechanical effects start to become visible, which is really neat. So in this case, it manifests in they glow in the dark, but under like black light kind of thing. So my quantum dots. So normally quantum dots are made out of like cadmium sulfide or cadmium selenide, and you can get them to go pretty much any color, but they're toxic as all hell. Whereas mine are made out of sugar, like ordinary table sugar, and truly I can make them out of pretty much any carbon source you give me. The caveat being you're overwhelmingly going to make blue quantum dots, just because that's the side, like that's just the color that likes to form, which is the reason that those are the ones that I've got on the site. Just because anything else you need like strong acid to do it, but I mean it's still easier to do than your like cadmium sulfide stuff, and it's not going to kill you. So, and what's cool about it, because it's carbon, you can very easily dope it so that it has other metals or like functional groups on its surface, so that it's really easy to attach stuff to it. So you could take my quantum dots and do a little bit of chemistry to them, so you can put targeting compounds on it or stuff so that it's easy to like get it to go into cells or whatever it is that you're trying to do with it. So you could use it for pretty much anything that you want a fluorescent particle to do. I mean, they're only like 3 nanometers wide, so they're real tiny.
So is the production method similar to the one that's used to make the fireflies? Is this the same?
No, God, no. Totally different. So it's take sugar, dissolve it in water, add some acid, and heat it up. You can do it on your stove. Like, it's dirt easy to do. I do it hydrothermally, just because I've gotten really good at hydrothermal stuff, and I have hydrothermal reactors, so may as well use them. But you can totally do it at ambient pressure on a stove.
So a hydrothermal reactor that's just a hot, wet box?
No. So it's a stainless steel. So you can make a hydrothermal reactor out of parts from like your hardware store. I bought mine online because I was doing it enough that it seemed worth it. So the difference being the one that I have has a Teflon lined container. So it's like a Teflon vessel that you put in this big stainless steel thing that you like twist down so it can be under pressure. And there's a lot less chance that it'll leak. Whereas the ones that I was making using like hardware store materials had a habit of like blowing a leak, and so they'd depressurize and then it would just burn and stink and be gross. But yeah, so it's real easy to do. I mean I made a whole video showing the process because it is truly dirt easy to do. And I'm going to be making another video showing how to make other colors other than blue, because I've done yellow, I've done green. I know how to make purple, but I've never tried it. And red's a pain in the ass, so I haven't tried that one. But you can make pretty much any color, just with a little extra effort.
Okay.
But yeah, so
with these what would you use these quantum dots for? These carbon-based ones. Why are the cadmium ones so much more popular?
Because the cadmium ones were discovered first, and they're brighter.
Okay.
And it's really easy to get a very wide variety of colors with the cadmium sulfide ones. It's literally just the longer you leave the reaction, the color will change. Whereas the carbon ones are a little more dim, and it's not a timing thing. It's a pH of the reaction solution thing.
Okay.
So yeah, it's just different, and the carbon ones were found later. But they're starting to gain popularity, and so anything you can use the cadmium sulfide ones for, you can use the carbon ones for. Which is everything from staining cells to solar panels.
Interesting. Is it possible that quantum dots form this way naturally in some conditions somewhere because if it's just heat, pressure, and pH?
Like, absolutely.
So yes.
Yes, absolutely.
Where has anybody found evidence of natural quantum dot formation?
If they were gonna look, I would check like hydrothermal vents. That's a really good place to find them. As if there's carbon near one of those, you're gonna form them. Yeah.
Don't some of those weird glowing deep sea fish have something like biosynthetic quantum dots in their skin?
Well, that's
I
almost.
might be wrong about that, but I feel like I remember.
Yeah, no, the glowing, anything, if it's glowing and it's in the ocean, it's a protein thing. Or it's some chemical, it's never quantum dots. Or maybe not never. Definitely not never, but I've seen no evidence for biological quantum dots being used for anything.
Yeah, in fish, my understanding is all of the glands that have glowing things in them, there's some kind of bacteria in there that makes a protein that's like luciferin or something like that.
Yeah, that's almost always how it goes. Or like GFP or any of those.
All right, cool. So fireflies, what are those about? And
so the fireflies, the fireflies are my first design for a nanorobot system. I was really frustrated with the way that medicine is done. So this is sort of my like, all right, well, here's my go at it. So the way they work is they've got a magnetic core, so you can manipulate them, and you can stick pretty much whatever you want to them. So be that a drug, be that a targeting molecule, whatever. So they kind of look like a dandelion, and the idea is when you give them a signal, it drops all of its little like seed-looking bits, and anything that's attached to the thing, like attached to the thing that gets dropped off, will end up wherever you leave, like wherever you have the particles in the body and you give them that signal, the drug is delivered right there.
So is the core ferromagnetic? What's going on there?
It's magnetite.
Okay. Is the signal like a rapidly oscillating magnetic field, or how's
You can use all kinds of stuff. You can use radio, you can use ultrasound, you can use rapidly oscillating stuff.
okay.
It really depends on the application. I like the idea of using ultrasound because then you can be visualizing what's going on, and then you just change the signal a little bit to get it to actually release.
Yeah. So how do you coat the magnetite with your payload? What makes
So that's sort of where all the chemistry and stuff comes in. So it's, and I mean I can't tell you exactly what chemistry is because patents and such. But the idea is so the way that we're doing it right now is it's a coating of a special silica compound, which and there's all sorts of ones that you can use. But they form like a monolayer around the iron, and with all the functional groups all facing out, so that you can then grow chains off of them. And then once you've got the chain, at the end of the chain you put a dendrimer, which are these really cool like branching molecules. And then the dendrimers can actually like bend and they can interact with their environment, and they can do all sorts of things. So you can either then chemically attach your cargo onto the dendrimer, or you can build the dendrimer to just wrap around your cargo temporarily, and then release it later.
Okay, so you're like using some kind of chemical vapor deposition to have the silica go on?
No, it's all wet chemical stuff.
Okay, wet chemical stuff. What happens when the fireflies like exude their payload? Do they just hang out with the magnetite and the like spiky silica balls in the tissue?
Well, the nice thing is because they're magnetic, you can then pull the cores back out. So you just leave the cargo behind and pull the cores back out. Although that's just version 1. Version like the next version, I'm going to make it so the cores can dissolve, and just be broken down, so that if any are left behind, that it's not a problem.
I mean, I'm imagining them inside a extracellular matrix between lots of different cells. What do you mean pull them out? Like with a magnet?
Yep. So the idea is I'm building whole magnetic arrays to control the things. So you can push and pull them throughout the body to wherever you want. And when you're done with them, you can pull them. Say you've got like an IV line to get them in, you can pull them right back out the IV line.
Okay. How are you going to test them on? What's your testing regimen like? And when you prototype these to a like sufficient quality that you think, okay, I want to start testing this in some kind of system. Would you start with a living system? Would you start with
so we're going to start with
non-living system?
well, so step 1 is do it in a test tube and see if you can actually get them to break properly. Step 2 is cell testing in like a little petri dish kind of thing.
Wait, why aren't they all going to clump together, and then like if they got stuck in your blood or in the passageway, wouldn't they block that passageway?
Really tiny. They're like really, really tiny.
Okay.
So that's
even though they're clumping,
you would need like an overwhelming large amount to clog something up.
Okay. You also want a really, really strong magnet to pull these guys around.
Yeah. Well, I mean, it doesn't need to be that strong. Strong is just faster. Yeah. I mean, it's a whole system. It's the particles, but then it's also a big machine to control the thing.
Right. So you make them in the tube, and then what?
Well, so we test them in like a test tube, make sure they break properly.
Right.
Then after that we go to cell testing, and then after cell testing we're gonna do it. We're gonna inject a little bit into a rat, and then see if we can pull it back out.
So, like you like a tissue culture, or do you mean like a cell culture?
Well, so we're gonna do just cell culture to start, and then if it's fine in cells, then we're gonna move to like a rat, like an actual like squeak squeak rat.
Okay. Squeak, squeak.
Yeah.
All right. What's the timeline on this like? Does it have a backseat now that supercapacitors are in the front burner?
Well, it would have had a front seat, but the overwhelming amount of bureaucracy and bullshit that I've had to jump through to get this working has been just like head desk worthy.
Well,
Like
because you're in Canada.
No, it's because I'm surrounded by idiots. So it started with, we had this grad student who was supposed to be helping us out, and rather than let us do the work in the lab, he insisted that he did everything and then promptly did nothing. And so we like check on him, we're like, hey man, did you get anything done? He's like, no. Well, it's been 4 months, what the hell? So eventually that got frustrating, so we fired him. And so then we started doing it on our own, and rather than and it was going really well. We were like a day or two off of finishing the prototypes when all of a sudden more bureaucracy hit, and my supervisor had to stop being our supervisor.
Doing this at a university?
Yeah, I was working at Carleton to get this done.
Okay.
But yeah, so
you were getting them to pay you to do the research,
or
or what?
No, so I had an agreement with a couple of professors so that I could use their lab and their equipment and materials and stuff.
But you're still retaining rights to all the stuff.
Yep.
Okay. But you're at a university, therefore bureaucracy makes you wade through it.
Yeah, and it finally hit a point where I was like, you know what? Fuck this, I'm over the bureaucracy. So I went back in, refined the chemistry to the point where I think I can make a batch in my lab, and that's kind of what I'm planning on doing. I'm waiting on one material left coming in the mail, and once it gets here, I'm gonna go for it and see if I can make a batch.
Okay.
Because yeah, I'm sick of waiting. I'm sick of twiddling my thumbs and just waiting for bureaucracy to resolve itself. So it's either I'm going to do it myself, or it's just getting put to the back seat until I get a lab where I can just do this properly. Because, oh boy, is this frustrating.
So back when you were 14, you were fixing computers in order to get money for the fusor. What do you do nowadays for research funding?
Well, so I've got a couple agreements with a few different people who are sponsoring me to do what I do. Because they see what I do and they're like, well, that's really cool. We need to take my money here. So it's kind of private investors, I guess, at this point.
Okay, excellent.
Hey, just because I missed the very beginning, I kind of understand your neutron source, but what is it? Deuterium tritium or deuterium deuterium? And also, like, what's the energy source to press it all together?
So the kind of reactor I was working on is officially called an inertial electrostatic confinement fusor. So it's got 2 grids, and you put a very high voltage between them, and so as the electrons move between them, it ionizes gas, and once the gas has a charge, it gets flung towards the middle, and when it collides, it fuses. So for a fusor, almost everyone uses deuterium-deuterium. Deuterium-tritium is essentially non-possible because getting tritium is like impossible. Especially at the amounts that you would need, since it's very highly regulated. But any idiot can buy heavy water and electrolyze it to get deuterium, which is basically how everybody in the fusion community does it, because it's real easy. Although for the reactor that I have in mind now, I want to see if I can do it with hydrogen boron, just because there's so much more power and it's aneutronic. So no neutrons, which is always good. Which is weird though, because then you've got a reactor that's producing 0 neutrons, so it's a lot harder to confirm that you're getting fusion. But it's also producing a lot more power. So you'd find out if all of a sudden power starts coming out of the thing.
I thought to do fusion you had to rip all the electrons off and fling them into
Yeah,
each
well, I
other.
mean that's what happens when it ionizes. You don't need all the electrons off. You need a electron off, just so the thing will fly at each other. And once it ionizes, most of the electrons go flying, just because they do not play nice when there's that much energy at like in the area. Somebody actually used a really nice phrase where it's like nuclear melting. So just the same way going from solid to liquid, the things kind of move apart. Same sort of idea. When you hit anything above about 5,000 degrees, all the electrons kind of melt off, and you kind of get the separation. But some electrons do tend to stay around the thing. Like it's hard to get them all off, because that's a lot of charge that's being exposed. So it's easy to get 1 or 2. It's hard to get more.
So I can tell, based on our conversation so far, that you're into science.
No shit, really.
Do you dabble in other fields like entrepreneurship or art or travel or music or dance? You know, are there other things that you do, or is it mainly
So
science?
had I not gone into science, I would have gone into art. I love art. I like specifically theater. I was a tech guy. I loved running tech on shows. I liked building sets. I loved painting sets. I like building props. Like I love just making stuff. That's really what it is. I make things. So when I'm not doing like hard science, I'm doing like I was making soap for a while. I really like making soap. I was.
What do you like about
Say again?
Why make soap? What do you like about making soap?
Because it's a little bit dangerous. It's a little bit chemistry, and it smells wonderful. And once because there's actually a lot of thought that goes into making a good quality bar of soap, and I found that one out the hard way. And so it was just interesting because I get to use all of my like chemical and science knowledge without the high risk of everything else that I do. Because it's really just simple and easy, and it's just kind of fun to watch the process, and I just like it. I just find it really enjoyable, and also it makes my lab smell just phenomenal, as opposed to the other thing. Like the heart smells so bad. Oh my! Like anytime I do decellularization stuff, it smells so bad.
What, from the rotting cells?
Not necessarily rotting, but just it doesn't smell good.
Doesn't smell bad.
Well,
Okay.
it's just meat in water. If it's not like cooked, it just does not smell good.
Vegetable. Does decellularizing vegetables smell bad?
No, those ones actually smell kind of like they smell really really nice. Like the strawberries smelled like sweet and like strawberries, but liver smelled like gross, just all the time.
Worst smells.
I couldn't hear that. What?
What's your favorite?
What, does the liver smell worse than a liver normally smells?
Yeah, because all the gross is coming out of it, so anything
Okay.
that was contained gets. Oh god, it's not pleasant. It's one of the reasons I won't do a kidney, because I've cooked kidney once, and as soon as I opened that package, I realized it was a horrible, horrible mistake because my entire like room just stunk. So I refused to go near it because it just everything smells like piss. So yeah,
Alright.
they
What-
smell not as
Everyone
bad.
what your favorite Soap fragrances?
Yeah, soap scent.
Favorite soap scent?
My favorite thus far, we did Star Anise like black licorice bar,
Ah,
and it was that one. That one continues to smell very, 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 very good. It was like activated charcoal, star anise, and cocoa butter. It was.
can we get a free sample for the space bathroom?
I barely have any left. I've only got like a couple of bars.
How long does it take to make well, how many bars do you make at a time? And how long does it take to make that many bars?
So I'll make like so I buy these like silicone like mini loaf things. So it's a loaf about yay big, and it cuts into about 6 bars. So I make about one of those at a time, just because I like to work small, because then I can kind of make all sorts of variety, and it doesn't cost like an arm and a leg worth of oil and hydroxide. So I'll make about 500 mils or a liter worth of soap at a time.
And how much and how long does it take?
Oh, it depends on it depends on the mixture of oils that you choose. If you add things like shea butter or cocoa butter or Crisco or that kind of stuff, it'll harden very, very quickly. And so, I mean, really, the whole thing is you get 2 liquids, heat them up to like between 120 and 130 Fahrenheit, mix them, and within 5 minutes it starts to go hard, and when it's like the consistency of pudding, you pour it out into the mold and you're done. It's super, super easy. Like that's one of the reasons I like it. It's easy. It's a little bit of chemistry, but it's still fun.
What's the cost of the materials?
It depends what materials you use. If you're using like high quality like olive oil and stuff, it's gonna cost you more than if you're using like your vegetable oil. But yeah, you can use anything. So if you're like a hunter and you've got lots of fat lying around, you can render a whole bunch of fat and use fat. If you got corn oil, use corn oil. Sort of depends.
There's a group down in New Braunfels that use hemp oil.
Yeah. Avocado oil. I just bought some of that.
That'd be expensive. I think avocado oil would be expensive.
Yeah, that'd be
Yeah, it's like the most.
I've seen the bottles of that in the supermarket, and I'm like, oh yeah, not using that. That's expensive.
Let's do some truffle oil soap.
That could be a luxury item.
Yeah.
It would be. It would also. Man, truffle oil is one of those things that nobody actually uses that shit in food except people who don't understand food. Just because the people who make truffle oil are perfumists. They're not cooks, because that's the whole point. It's meant to smell and whatever, but an actual like chef will not be caught dead using that stuff unless they're trying to like make it sound fancy.
What would be a good oil for us to get a hold of, Mac? Make soap with?
Just regular vegetable oil works really well. Crisco, honestly, like big old bar of Crisco.
Got a lot of Crisco.
$5, and it works beautifully.
Gallon of Crisco.
What was the reason for that? Buy Crisco in bulk?
Yeah, I mean, I try to buy things in bulk, save money. Yeah.
Let's make soap.
Yeah, man, I would highly suggest it. Soap is
highly
a very, very fun thing.
I have a few bars of Irish Spring. Can you make something as good as that? Think that'd be hard?
How hard is it to make soap better than what you get at the store?
Well, it depends what you're buying at the store.
If you've never.
Like, it depends what you're buying.
He's saying Irish Spring. Have you heard of Irish Spring?
So liquid and gel soaps are a totally different beast. Because then you're not using like oil and hydroxide. It's like polyethylene glycol, SDS, EDTA. Like it's a whole like shopping list worth of different stuff, and there's a lot of like care and attention has gone into making shit like that.
Why do you put EDTA in soap?
Just to kind of chelate ions off your body.
Oh.
Yeah, it's just a general cleaning thing. Like when I was doing the decellularization, you use a little bit of EDTA to help collect up some of the ions that are coming off of things.
Do you have anything cool to show us, like in your room or your house?
Not overwhelmingly. All the cool shit's downstairs.
Is your lab? Can we go on a tour of your lab?
I don't have a laptop, so no, because I've only got a desktop,
right.
So I'd have to like get an extension cord and like carry it around my desktop, so that wouldn't go well. Yeah.
Great job.
How many people work with you on your experiments? Is it mostly yourself or 10, 15, 5, 3, 2?
So it's overwhelmingly just me. Like I've got a guy who, like, I've got a couple of friends who will hang around while I'm working and like, here, hold my beaker. But for the most part, it's just me.
Why do you think that is?
I haven't really found anyone in the city who's interesting. At one point, I was working with another guy, and this is the funny bit. In August, like he was the guy I started the Thought Emporium with, and everything was going great. You know, things were starting.
I remember those two guys that started the Thought Emporium.
Yeah, and then in August he goes, "I don't think this is going anywhere. I quit."
Okay.
Yeah, which was basically, to which I basically went, well, fine, fuck you, and so I created the nanites and everything else, just I think sheerly out of spite at that point.
Nice.
I was like, what? Fine, fuck it. If you quit, I'm gonna change the world and make you an idiot. Yeah, so he's the only guy that I've like really worked with in that sense.
Okay.
I've got one guy who I work with on the nanites. But other than that, yeah, no, it's overwhelmingly just me.
So, like halfway between the quantum dots and the nanites, I was just, I've read about people making gene guns before, and how you put in tiny like gold nanoparticles or nickel or something, and you shoot them at things.
Yep.
Can we use the quantum dots, or theoretically these nanites that you're designing for gene gun usage, and then like
I wouldn't advise that. It's the wrong sort of thing. Gold works really well because you can get nice like round particles. You can get and it's really inert. So once you shoot it into the thing, it'll kind of just ignore it. Whereas the nanites are meant for interaction. They're not meant to just be left there. And the quantum dots are just too damn tiny. However, I mean, because I created a way to extract DNA in about 5 minutes.
With the quantum dots?
No, it wasn't with the quantum dots. It was a whole different system. It's magnetic silica.
Okay.
So it's tiny little silica beads with a magnetic core. So you basically take your sample, lyse it open, and dump the beads in with glycine and potassium chloride. Give it a second, and then you use a magnet to pull them out and drop it in like fresh like buffered solution or whatever, and the DNA just drops right off. So in like 5 minutes, you get your sample.
That's faster in time, but does that cost financially much more than the standard
like
chemical series of? Okay.
No. To make the process that I use to make that stuff, I could make you a bucket of the beads for like $10.
Okay. Can we do that over here?
Potentially. Yeah. I'd be okay with that.
Based on the beads. I've never used like beads for anything before. I had some glass micro bubbles and that's the closest I ever got to using beads for anything. So I would love to try that out.
Yeah. If I've got a little bit of time, I can see if I can make you a batch, and send it down to you so you can mess around with it and see if I can get it working.
I do have a batch if it only costs $10. We have a lab.
Well, it's $10, but it's you need a hydrothermal reactor to do it.
Okay. Maybe I should get a hydrothermal reactor. Based on
Probably.
talking to you, it should be.
You probably. I mean, it's a useful piece of kit. But also, it's been a long time since I've made them, and because I've had time to think about it, I've got a few improvements that I think I could do. So I think I want to, like, if I was gonna let you use them, I kind of want to use it as an excuse to see if I can improve the recipe. And then I can just ship her down to you.
Right.
Also, because I haven't decided what I wanted to do with that yet. Because I could totally like patent it, or I could sell it, or whatever. But that's one of those that I'm very much tempted to just release how to do that, and be like, okay, world, here, enjoy. But I haven't really decided what I want to do with that yet. So that's the only reason I'm hesitant to tell you how to make them. Because it's a method, it's not a unique thing. There are other systems exactly like that you can buy. The only difference is they'll sell you a vial like that big worth of beads for $400, whereas like I can whereas mine's dirt cheap. So that's the thing.
But are they less precise in diameter or anything like that?
No, it's fairly random, but they're also very, very tiny. Like it's all like, you know, a couple of micrometers, like real itty-bitty stuff.
Okay.
Actually, you know what? I may have a vial of them hanging around. Give me a second. Yeah. And a magnet.
Lots of information. It's awesome. I'm kind of like too tired to comprehend all of it. But this is really, really, really interesting stuff.
All right.
I did engineering in high school for 2 years, and I miss it a lot. And this is really fun.
Nice. What's up, Justin? How are your beads?
All right, so I don't know if you can how well you'll be. So you can kind of see them.
Are they floating in water?
Yeah.
Okay, I can see them. Yeah. I can see that.
Yeah.
Those seem like precursors to the hematite beads.
No, this is the final. This is like the final DNA extraction beads. This is exactly the.
I mean, like creatively precursors. Maybe you were doing that before you were out the Firefly project.
Yeah. This was my like first like useful magnetic thing that I can. This was what happens when I go to a genetics class once. I was like sitting there bored, and he's like telling us the different ways to extract DNA, and I'm sitting there looking at it going, well, those are kind of shit. I could do better. And so I go up to him after class, and I'm like, so here's my idea. What do you think? And he goes, well, if you can do it, you can come into my lab and try it out. I'm like, okay. So I come back. So I go home, make the thing, and then go to him tomorrow, and I put it down on his desk and go, here, I did it. Can I try it out? He goes, absolutely. So go into the lab, try it out. Sure enough, works great.
Nice. So I've heard that beads are the best way of extracting DNA, but how do they work? What's on the outside that makes the DNA want?
It's exactly the same as like a silica column. The only difference is because it's a magnetic bead, you can just drop it in and pull it back out, rather than having to run like a centrifuge or whatever.
Okay, so it's what the silica, does it have any special electrical properties that interact with DNA, or is it just?
So when you add lots of salt to the solution, like specific salt to the solution, there's a slight charge on the silica that's opposite to the charge on the DNA, so the DNA will stick. but it only does that under high salt conditions. So
Right.
when you want it off, you just put the bead into low salt conditions, which then masks the charge on the DNA, and so it comes off.
Okay. Yeah, this is like the thing where clay particles that are porous can have DNA like trapped in them and around them for extremely long periods of time and have totally independent conditions from all of the other clay particles in like salt water or something.
Yeah, and
Yes,
it's one of the reasons that you can like sample beach sand and find DNA, because it's salty and it's silica. So they actually found like old ass DNA in beaches, just because, you know.
that would be fun.
Yeah.
We should go sequence some ancient beaches. Or like verbs. Have you heard of verbs? They're layers of pollen that accumulate in sediment, and you can take a core of a lake and check them, and then sample out of each verb, and you can find out like what the ratios are of different kinds of tree pollens that were that year or that 100 years.
I hadn't heard of that, but that's actually really
It tells you about what the climate was like there.
Yeah, that's really cool. I mean, there's all kinds of like core sampling that you can do that can tell you some old data,
Yeah.
which I think is cool. I mean, like they found a really old bit of like graphite or something, and there was some evidence that it was like biologically derived, even though it was just ancient,
Right.
which I thought was very, very cool.
Nice. Excuse me. Are you working on any bioreactor projects right now?
Not really, just because I don't have the time or the right kind of space for it. It's really just been batteries and nanites just till I get to summer, and then once I'm in Chile, then all the fun shit happens.
What's happening in Chile, Justin?
Oh, I don't know. What could be happening in Chile? No, it's the exosphere, the whole exosphere thing. I'm very excited.
Okay, why are you excited about exosphere? What does it mean to you?
Well, I mean, we have some projects that ought to be kind of interesting.
Okay.
Yeah, we're gonna.
Who's we?
Well, I've been talking to Glims, and yeah, well, I mean, he asked me, do you have any crazy ideas that we could do? And I'm like, yes, I do.
Lots of them.
Lots of them.
I've got a whole.
Yeah.
Actually, I've got 10.
Yeah, so it's this crazy ass bioremediation project thing.
Okay.
I'm super. Because I don't know if I should. I don't know if I'm supposed to be telling anybody yet. I probably can't. I don't think it matters. But
Totally don't you.
Yeah.
It might. I don't know.
Yeah, I don't think it does. It's just kind of like, but we're gonna see if we can grow an island.
All right. Do you want any? We're gonna have a big culture of plastic eating fungus over here. Would you want to?
That's what that's for.
Okay, great.
Yeah, if he asked you for that, that's what that's for.
Well, I mean, I offered it.
Oh, okay, that'll do it. But yeah, so if he mentioned that, and so we're like, yep, I'm gonna work that right in, I think.
Okay. So, but what makes you want to go do Exosphere? Is it just because Glims will be there and he asked you to do cool stuff with him, or?
Partially that. Partially, I was really underwhelmed with the genetics program at my school. Like so bored.
I bet Gabriel could teach you some genetics.
Well, that's the idea. So the exosphere is sort of rounding out and kind of finishing off my body of knowledge that I need, because genetics is the one thing that I really want to play with, and I just don't have. I just didn't have the practical experience with it because my school just doesn't freaking teach it properly.
Right.
3 years.
Most don't teach properly.
Yeah, like 3 years worth of genetics, and they're still teaching us about fucking Punnett squares. And I'm like, are you kidding me? Like, fuck. So, yeah, it's frustrating.
Well, okay, I gotta go. I'm getting hungry.
Josh is getting hungry.
Best of luck to you if I never meet you again. You're really, really smart, and you know way more than I do right now. Just best of luck to you. Keep on working and keep on designing awesome things.
Thank you. I intend to.
Yeah. How many times a week does this a month does this group meet?
Dude, so actually we're here every day working at this lab.
Okay.
And events probably 2 to 3 times a week at this point.
Okay.
Like the meetup, it's got a bunch of events on it.
Okay.
Next week we're gonna be I'm going to do night vision eye drop for the first time.
Okay.
And I'm going to put them in my eyes.
All right. I'll definitely try to come back and
Oh yeah.
Yeah. Talk more
Thanks for coming, Josh.
get more knowledge about this stuff. Yeah. Thank you.
All right.
Thank you. If you need helpers, I know a few guys in Ottawa that might be good helper people.
All right.
He's got helper people in Ottawa for you.
Yeah, well, I mean, I won't be here long. I got, like, till the end of June, and then I doubt I'm coming back, so. Thanks for the offer, but I don't know if I'll be here, unfortunately.
Moving to Chile.
Yeah, maybe. I don't know.
Maybe I'll see you in Chile.
Oh yeah, Trevor might be there with me too.
Ooh, fun.
His brother lives in
Argentina.
Argentina.
Yeah, if this
All right.
island thing goes well, I intend on staying in Chile and growing myself a country.
Oh yeah. At that point, we're just going to find out how to make it grow as fast as possible, and then unleash it in the ocean.
Basically, yeah. And the way I see it going is I want to grow a little like archipelago worth of islands, and just set up camp over there.
Man, so back when there's this volcano that appeared off the coast of New Zealand that I am really into, and it made like, I don't remember exactly how big it was, but it was something like 10 by 10 square kilometers. It made a pumice raft that was that big in like 5 days, and then the volcano just went away. And I thought that this is a great place to study biology. Just watch land that was totally sterile get made, and then find out. Just watch it biologically.
Mm-hmm.
That I feel like there'd be so many great insights that come from that kind of project.
Yeah, there've been a few things like that where like an island will pop up and then people just kind of watch it as it grows, because like birds will drop seeds and soil will start to form and lichens will start to form and grow and all that kind of stuff. And eventually you get like a whole. I mean, there was one island that was pretty barren, and I think it was Darwin and a friend. Basically just threw every species they could at it and just started seeding it with everything they could, and now it's a totally like self-sustaining ecosystem of just the weirdest, most random shit. So yeah, this is a cool biology when you're
You could like get a bunch of soil there that was the same properties as Martian soil, and then make a tiny Martian-like microbiome on an island.
Well, it would never be Martian-like because.
No. I mean, just the soil.
Yeah, I mean, it'd still be difficult though because it's still Earth bacteria and stuff. So no matter how Martian you try and make it, all of the Earth stuff is gonna just wreak havoc on it.
Yeah, that's why you sterilize all the soil, and then you gene sequence to find out what.
It's a whole island. It's a whole island, though. You can't sterilize a whole. I mean, you can, but like, actually, you can't. Microorganisms will always out-edit you and always out-compete you. So you'd never be able to keep it sterile, and so long as it's exposed to the atmosphere, it's constantly being bombarded by Earth stuff.
Yeah, I'm saying that's the point. Like, examine
and just see what forms, kind of thing.
Yes.
That could be. I mean, yeah, it could be interesting. Yeah. I'm really. One of the things that I really want to do. I just haven't gotten around to it. I should. As I was learning all the hydrothermal stuff, I realized that you could probably create all the things that you need for life hydrothermally. And when I looked it up, sure enough, you absolutely can.
Right.
And there was a couple of experiments that are building like special hydrothermal reactors, like way more complex than the stuff that you can just buy, kind of thing, where it's got like layers and gradients and stuff. And yeah, almost instantly the thing started spewing protein out of nothing.
Well, we should put thermal reactors on Mars and just wait.
Yeah. Well, I mean, that's the thing. Like, I'm pretty much at this point. The thing that I'm most curious about is basically any other planet that is got water and has alkaline hydrothermal vents.
Europa.
Yeah. Right. I'm fairly certain there's got to be something on Europa if it's warm enough. Like, I would not be surprised at all if we got there and like sampled some shit and we're like, yep, there's okay, some sort of microorganism.
All right, Austin, how are you doing over there? Microphone's off.
I'm doing fine. Music's keeping me busy. Our client, KQI, they're keeping me busy. I hope if you decide to go through with your project, I'm looking forward to working on that. Still been thinking about it a little bit. But,
Sweet.
I've been doing a little math again. The one thing I was thinking about the other week that got me wanting to start modeling stuff again is like, I was playing my guitar and I got when a string vibrates, it drives the guitar body a little bit, which also will drive the other strings.
And
I think that if strings are too out of tune, this doesn't happen, but especially when you play power chords, I think if they're a little out of tune with each other, it doesn't sound as out of tune as it should, and I'm wondering if that's because of they're all co-driving each other. And so I went back and did all the basic vibrating string solutions again, and I tried to analytically solve a driven vibrating string, but I'm going to keep taking a look at that, but I don't think that can be done analytically. There might be a differential equation solution method that I either don't know or have forgotten about, but I'm pretty sure I'm going to have to go to Java to get some insight into that. So I am curious how vibrating strings co-driving each other. What I would like to do is set up the exact same conditions in two cases, one where they're all independent and one where they're driving each other, and then have it output the waveform of each, and then do various kind of analysis of each and see, quantitatively what the difference is.
Yeah, that seems like it would output a parameter that would be useful in modeling the timbre of the instrument. Also, like all pianos use aliquot string, where every key hammers 3 different strings, basically. And probably using that, the string is driving the body, which drives the other strings. Okay. Sweet. Well, Justin.
One of my predictions is that one of the biggest things will be phase, in that at first the strings will be randomly phased with one another, but then the different overtones and respective like octaves of like an overtone of one string, and then an octave of it that is also an overtone of another string, like they will fall into some type of regular phase pattern fairly quickly, like probably within less than a second. I think I can kind of hear that, but at the same time I don't. You can't exactly hear phase, but you can hear the difference between constructive and destructive interference.
Right.
I don't think they'll line up in phase, but I think they'll tend toward like 90 degrees or something like that.
Okay. Yeah.
Cool. Well, anyways, I'm getting quite hungry, so I kind of want to go make food.
Justin, we're finished here. Thanks for hanging out, chatting. It's been good to meet you for the first time. I will apparently be living with you for 2 months in Chile.
Indeed.
So we'll probably get to know each other a little bit better after that.
Ought to be fun. I'm excited.
Yeah.
Very excited.
Thanks for.
Nice to meet you, Justin.
Wait, I didn't hear that. What?
It was nice to meet you. Nice to meet you, Justin.
You too.
Keep it up. How old are you?
21 next week.
Oh, okay. Yeah, that's pretty impressive, man.
Thank you.
Woo!
Yeah, there definitely, like, somebody at one point, I think it was right after Body Hacking Con, somebody asked me, so what have you been up to for the last couple of months? And when I, like, wrote out the list, I kind of looked at it and was like, huh, well, shit. So, it's definitely, it stays interesting.
Yeah, man.
Yeah.
You got a amount of time. You better make it fun and interesting.
Right? Like, you got one shot at this, may as well make it fun. So, anyways, I'm gonna head out. This has been fun.
All right. See ya.
See ya.
Bye, man.